Hello and welcome to a Saturn Online presentation entitled Harnessing Combustion for Heating. And what we're going to do is talk about the flame and the combustion chamber and just what happens there. We're going to isolate this very, very important area and talk about the flame, the flow of combustion air to the flame, and the flow of exhaust gases out of the combustion chamber. So to start off with, we have a combustion chamber that has no opening except it has a gas line in for a burner. We light the burner, and then what happens is the flame goes out because it rapidly uses up all the air inside the box and is unable to burn. And if the gas were to continue to flow, the pressure would just equalize between the gas line and the combustion chamber and nothing would happen. Okay, now let's put two holes in the combustion chamber. We have a hole around the pipe that goes in for the burner, and then we have a hole up high here to let the exhaust gases out. Now this is a very important evolution from here to here because now we're able to have a flow of combustion air and gases through and around the flame, in one end and out the other. And this is what we need for sustained, predictable combustion, combustion that we can actually use for heating. So what we have is just a gas pipe, and we light the flame, and we have what's called a luminous flame. And a luminous flame is a yellow flame. And natural gas was first used to provide light. And the yellow flame provides quite a bit of light. It also provides some soot. And the soot is also a sign that carbon monoxide is being produced. And carbon monoxide, as we know, is the product of incomplete combustion. So we have soot and carbon monoxide happening here because the flame is not a blue flame. The flame is a luminous flame. We have the flow of combustion air into the combustion chamber and a flow of the exhaust gases out because the pressure of the atmosphere. You've got this atmosphere that's 20 or 30 miles high that's bearing down on us, okay? And when we burn, gas and air, we're heating all the molecules that go through that reaction, and we're driving them farther apart, which means that they become less dense than the air in the atmosphere, and they want to rise. The reason why they want to rise is because the atmosphere is pressing down, and that pressure exists right here, and that pressure is a positive pressure. And whenever I say positive pressure, I'm saying, you should say, well, with reference to what? Well, with reference to a negative pressure over here. So, gases will flow from a positive pressure to a negative pressure. And that's exactly what we want them to do because we need a flow through here. We need combustion air to be continually added to the flame, and we need the exhaust gases to be removed. Because if the because if the combustion air were not added continuously, and if the exhaust gases weren't removed continuously, the flame would go out, wouldn't it? So positive pressure here because of the atmosphere, because of all that weight of air bearing down on us. And we have a negative pressure here because the flame has heated the gases that are going through the combustion process. As the gases are heated, the molecules run into one another, they get further apart. When they get further apart, that means they're less dense. And if they're less dense than the air around them, or the air in the atmosphere, then they will move out and more atmospheric air will move in. We'll have a continuous flow. That's what we want in the combustion process. We would like to have a continuous flow of combustion air and exhaust gases through the process. That's what we need to have predictable, useful combustion. Now, let's modernize the combustion a little bit, because now what we're going to add is primary air. And with primary air, okay, we have a gas pipe right here. And the gas pipe has an orifice in it. And the gas pipe has pressure in it from the line, from the gas line. So the gas flows through the orifice. And as it flows through the orifice, it draws air in with it, into the burner. So it's drawn into the pipe, and it gets to mix. The gas and the primary air mix together. And so you end up getting a flame that is a more sophisticated flame. It's a blue flame. Got primary air coming in, being mixed in the burner. Then we have secondary air that's coming in just through a hole here in the burner. So part of the gas is being burned with the primary air. And there's kind of an inner mantle here. So you'll see, you can often see in a good gas flame, you can see that there's at least two parts of the flame. You have an inner flame and an outer flame. This primary air and the gas are burning here with this inner flame, and then the secondary air comes and surrounds the flame and helps the rest of it to burn. There's a more complete combustion. We said with this luminous flame that there's some soot and carbon monoxide. With a good blue flame, there's hardly any carbon monoxide and no soot. And that's because we've got primary air. That's all about the primary air. And a guy named Bunsen, a German named Bunsen, invented this. And the Bunsen burner, which you may have used when you were in high school, is a product of this mixing of the primary air with the gas in the burner before that mixture comes out the end and creates this blue flame. And again, we've got a flow of air coming into the combustion chamber and the exhaust gases going out. And that's happening by atmospheric pressure. So we talk about atmospheric pressure, and actually we more often talk about atmospheric draft, because that's what we call the pressure in a combustion chamber or in a venting system. We call it draft. We don't call it pressure. So the pressure that moves these combustion gases in and the exhaust gases out is actually called an overfire draft, because it's a draft over the fire. Across the fire, there's a pressure difference. And the pressure difference, as we said before, is positive here and negative over here. And the difference is because the gases right here are hot and they're less dense than the air right here. So that gives you an idea of kind of an evolution. Right here, we have no flow. I mean, if this were a house and you were burning gas in the house, eventually you'd use up all the air in the house and you'd suffocate. And I mean, that's happened to people. And in the early days, I mean, with the Native Americans had teepees, and they had holes in the top of their teepees because they wanted to have fires in their teepees. And other types of early people had either holes in their roofs of their houses, or their houses were leaky enough that air would flow in and the gases would flow out. And it was one of the reasons why life expectancy wasn't so high in those early days. But now we've got a more controlled type of combustion. We've got an atmospheric flow of gases across the heat exchanger. We've got an atmospheric flow of gases across the combustion chamber. And so most of the appliances that we see are this type of appliance, which is now considered as kind of an obsolete technology.